Hi everyone, we are here in the second last lecture and we will introduce the last topics of the course, which are Laplace transform and how to solve some ODEs with this new object that we are going to study, these Laplace transforms. Okay, so let's start. As usual, we will give the definition of this new element, the Laplace transform, and then we are going to see some properties of this new object, and then we will have the method of the Laplace transform to solve some ordinary differential equations. Okay, so let's start with the definition. Here, so to fix notation, usually we were calling like f of x, like the main variable was x, but now in this new setting we can call it f of t. This is just to fix notation. If you prefer to write f of x is completely fine. F of y, like, you can choose, but to be consistent in the rest of the lecture and the next lecture, we will fix this notation. So f of t for the function defined on this interval 0 infinity, so t is greater or equal than 0. Okay, so once we take this function and we compute its Laplace transform, which this procedure will give us a new function. So we choose as the new variable the letter s. Again, t, s, w, any letter should be fine. We are just fixing notation. So we will start with the function f of t, defined it for t greater or equal than 0. We will see how to compute the Laplace transform of this function, which will give us a new function with the variable s. Okay, so now the Laplace transform of a function of this form, f of t with t greater or equal than 0, is given by this formula that we have here. The integral from 0 to infinity, so all the possible t's, and we multiply this function for this by this exponential to the power minus st, where s in principle is positive. Maybe in some cases we have a smaller range for s, but in principle is a positive parameter. And we will use this notation, L of f of s. Okay, so this notation will mean the Laplace transform of f at s, where s is in principle positive. Okay, some comments about this integral. This integral will be finite if this function f is slower than an exponential function, which means that this integral is finite if f does not grow faster than an exponential function. Okay, so we will see some definition related to this property, but it won't be super a key element of the method that we are going to use to solve ODEs, but anyway we have to talk a bit about it. Okay, so we are interested in those type of functions f where we have this exponential order, and we have a definition. We will say that a function f is of exponential order if the absolute value of f of t is less or equal than some number m times the exponential to the power a times t, where these guys, a and m, are positive numbers, okay? So basically our function would be of exponential order, where when we can estimate it from above, where its absolute value, by an exponential function, okay, with these guys positive. Okay. Then some examples, and this estimate we have it uniformly in t, which means like for every t greater or equal than 0. Okay, so some examples. This function f of t equal to 4 times cosine of 3t, where t is positive or 0. If we want to prove that this function has exponential order, verifies this condition, we need to find these numbers. We need to compute not compute, but we need to estimate the absolute value of the function and try to find something like this with an exponential and some numbers, positive numbers around. Okay, so here in this first example, for instance, when we compute the absolute value of f, of course we can split the absolute value with this product, the 4 and the cosine, and so we have the absolute value of the cosine here, and 4 is positive, that's why it's outside and with the absolute value. And now we know that the cosine function has a maximum at 1, so we can always use this property that the absolute value of the cosine is less or equal than 1, no matter the argument, like for any argument. So we find a 4 here as an upper bound, and we can think of this 4 as our m equal to 4 and exponential to the power 0 times t, because when we have 0 here in the power, then this number becomes a 1. So this function, that maybe in principle doesn't seem to be related to an exponential function, is anyway of exponential order, because the definition of the function of exponential order is just that the absolute value can be estimated from above with an exponential function with these type of numbers like m and a, positive numbers, or 0 is also allowed. Okay, so second example, f of t equal to exponential to the power 5t with t positive or 0. And here maybe it's quite easy because we can take m equal to 1 and a equal to 0. Sorry, 5. And we have our the absolute value of our function is exactly the function, because this is a positive function. And here we have our m and our a. So this is a function of exponential order. Okay, for this type of functions, we know that the expression, the definition of the Laplace transform will be well defined, finite. The integral will be finite. But this condition is sufficient for having this Laplace transform finite, but it's not necessary. Okay, we are not going to enter into details, but it's good for you to know that sometimes in math we can give some necessary conditions and some sufficient conditions, but they might not coincide. Okay, so in this case we are given only a sufficient condition, which means if I have a function f of exponential order, I can say that then the Laplace transform will be well-defined and finite. But it might happen that I have a function that I can compute the Laplace transform, and we have the Laplace transform finite, but this function is not exactly, of exponential order. And that means that the condition is not necessary. I might have a couple of functions where I can compute the Laplace transform, and those functions are not of exponential order. However, if we have this class of functions of exponential order, then for all of them, I can compute the Laplace transform and I know that it's finite, okay? Let's continue then. And let's compute some real, so far we only checked this definition and we were practicing with the definition of a function being of exponential order, but let's now compute some Laplace transforms. We are not going to check if they are or not of exponential order, also because one of the reasons is that maybe, we just saw that maybe it's not a necessary condition. So these functions might be exponential order or might be not, but we are not going to check that. So let's try to compute directly the Laplace transform using the definition that we have, as usual. We start with the definition and it's the only tool that we have so far, so we just try to see what we can do with only the definition. The easiest example, f of t equal to 1 all the time for every t, so a constant function equal to 1. We want to compute the Laplace transform of this function, which, remember, we are fixing the new variable as s. So let's use the definition, which is the only thing we have so far. So by definition, this new element that we are working with, the Laplace transform of this function at s, is the integral from 0 to infinity of our function times this exponential to the power minus s times t, where in principle s is greater than 0. Okay, in this case, that is our first example and is the easiest one, we have the function equal to 1, just the number 1. So an anti-derivative of this function, the exponential, is this expression that we have here. And remember that this means when we are working with improper integral like this one, because we have an infinity here, this notation means that we have to take the limit here of t when t goes to infinity, and okay, we can evaluate here at t equal to 0. Okay, and we have this factor 1 over minus s that we can put here in the front. So the limit of this function is 0. You can compute that, you can check that. And it's important here that we are using the sign of this parameter s, because s is positive, okay? And this number is just 1. This computation is just 1. So what we have here is 1 over s. And we just compute our first Laplace transform here. The Laplace transform of the function all the time 1 at s is just 1 over s for s positive. Okay, second example. Again, we are just increasing the difficulty here. We jump from the constant function 1 to the other easy function, just t, the identity t. So f of t is equal to t. Again, we need to compute the Laplace transform and we only know the definition, so that's what we are going to use. So the Laplace transform of this function at s is the integral from 0 to infinity of the function f times the exponential to the power minus s times t. Now we replace our f for t because that's what we have here. and try to compute this integral. As you can imagine, we are going to use integration by parts because we have a polynomial of 1 degree, only 1 degree equal to 1, and an exponential. So we can call this like u, and then the derivative of this is just 1. You can do this, complete the details later, but an antiderivative of this whole thing then is this function here. It's just using integration by parts. Again, this notation here means that we have to take the limit in infinity and to evaluate in 0. Okay. And so, evaluating in 0, we get here. So, evaluating in 0, we get the limit. And then, since we have this t here multiplying, the value at 0 disappears, okay? Then we have plus 1 over s, and this green piece, this part of the integral is exactly the exercise that we did before. It's the Laplace transform of the function 1 at s. You can check it later, but it's exactly like that. So we know that is 1 over s. Okay, so then we have to compute this limit, and we can use L'Hopital rules. I don't know if you might remember it from the lecture 6 and the auxiliary notes. So let's write the limit, which is here. We can, this parameter 1 minus 1 over s is just a number in this limit, so we can put it out of the limit, and then this is what we need to compute. To check that we can use L'Hopital's rule, we can rewrite this expression, because this minus means exactly that we can put the exponential in here. And then we have this indetermination, right? When t goes to infinity, this goes clearly to infinity, and also this piece. Here we are also using that s is positive, okay? Now we have this indetermination, and we can use L'Hopital's rule, which means, okay, you can differentiate up and down, and see if you can compute this new limit with these new two functions. And now we have something simpler, because here we have a 1, and here we have this expression s times the exponential to the power s times t. And now we can compute the whole limit, because this piece goes to infinity, and then the whole function goes to 0, okay? So now if we go back to the computation of the Laplace transform of our function f of t equal to t, what we get, here there are the previous calculations, right? And then we got this limit plus 1 over s squared. So we just compute the limit, that it was equal to 0, so we get this 1 over s squared. And finally we get then this formula, which is, okay, the Laplace transform of the function t at s is exactly 1 over s squared for s positive. Okay, third example. We are increasing the difficulty, right? With our first example was the function 1, second example, function t, third example, this exponential. Well, this alpha in principle is any number, and we might see that this alpha forces us to do some, to change the range of s. Okay, again, we only know the definition, so we use that. which is the integral from 0 to infinity of the function f times this exponential. Now we replace the function f, which now is another exponential, and then we are lucky to, we can take this t as a common factor and rewrite this exponential. And in the case that alpha is not s equal to s, we have this antiderivative. And again, this notation means you compute the limit for infinity and then you evaluate at 0. Okay, and that's what we have here. This number here, we put it in front because it's a common factor. And then we have to compute this limit, and this is exactly 1. Okay. Now, the value of this final number that we got here, or function that we got here, depends on this limit. And now is where this alpha will affect our answer. So this limit will be is exactly 0 when s is greater than alpha, because we have this type of exponential. Okay, and it's infinity when s is strictly less than alpha, and it cannot be equal to alpha because of this step. Okay, so if we want this Laplace transform to exist, we are going to reduce the range of s. In principle, s was just positive, and now we say, well, we don't know this alpha, but not only s should be positive, also should be greater than alpha. So, going back, now we know that the Laplace transform of the exponential function of this power, alpha t, at s is exactly this guy, 1 over s minus alpha, but now we know that s should be also greater than alpha. So here we have, this would be 0 in this range. So then we have minus times minus. So remember, the enemy of my enemy is my friend. It's like, okay, minus times minus is positive. So that's why here we don't have a minus. Okay. And we also know that this expression is not finite for s greater, smaller than alpha. Okay. Fourth example. The function t to the power n with n like 1, 2, 3, 4, etc. So for n equal to 1 was example 2, right? And then for the rest, what we can do is integration by parts n times. We can call like u of t to the power n. So the derivative would be like 1 power lower. And then once we have that expression, we can, for the second time we use integration by parts, we can call u equal to t to the power n minus 1, and then the derivative would be 1 power lower, and so on and so on. So when we do parts like 1, 2, 3, n times, we finally get this expression, and we will find this Laplace transform. But instead of doing that sounds like hard work, we are going to borrow some properties of a well-known function, well-known in mathematics, let's say. So we are going to introduce this function, gamma function, and we are going to use it to make it easy, this computation. So the gamma function is defined here in any positive x is the integral, so this is the definition, this is the integral from 0 to infinity of t to the power x minus 1 times the exponential to the power minus t. Okay, and this is the definition, and the properties that we are going to use are these two, but mainly this one. So some basic properties are, okay, if I want to know the value of the gamma function in x plus 1, then that's equal to x times the gamma function at x for x positive. And you can prove this here by integration by parts. Then in the particular case where this x is an integer, we have this property, okay, and it's just a consequence of the first property, but iterating that feature. Okay, so now we are going to compute the Laplace transform of this function t to the power n, or more general, t to the power alpha with alpha greater than minus 1. And this range has to do with this property that we have here, because the gamma function is defining for positive numbers. So then if we want to compute gamma function in a number plus 1, we need this number plus 1 to be positive, and that's why our alpha here will be greater than minus 1. Then alpha plus 1 is positive. Okay, so using the gamma function for this more general function, t to the power alpha, again, the definition is just put the f here. And now we use this substitution to try to get something similar to the gamma function. So here we have s and t, and we change that for tau. Change that meaning doing this substitution that we have here. We say like, okay, tau is equal now to st. So the differential is s and differential t. And then we have we can divide pass this s to the other side of the identity, and we have this. So now our t to the power alpha becomes our t to the power alpha becomes this tau over s to the power alpha, and the exponential is of minus tau. And just pay attention to the limits of the integral. So when t is equal to 0, this expression, so tau is equal to 0, so we keep this limit. And when t goes to infinity, then tau also goes to infinity, and here we're using that the s is positive. Okay, so we get this expression. And this 1 over s comes from this substitution here, okay? Let's continue. So this integral depends on tau, right? So we can put this s to the power alpha out of the integral, and we get this. And to be similar, to try to find this gamma function, if you remember, the gamma function was here with something like, well, the integral, maybe I don't write everything, but was something like the integral from 0 to infinity of some variable, x minus 1, and exponential, right? So we need that minus 1 in some sense. So a normal trick in mathematics is, okay, I need a minus 1, so I put it, but okay, I want to keep the identity, so I put a plus 1 too. And this is exactly